So, you know how we all imagine gravity as this invisible force pulling apples off trees or keeping planets in orbit? Well, Einstein flipped the script with his general theory of relativity. He said, hang on, gravity isn't some mysterious force. Instead, it's all about the way mass warps the fabric of the universe itself. Picture this. You're at a party with a trampoline. Toss a bowling ball in the middle and suddenly the surface curves. Smaller balls roll toward it, not because something's pulling them, but because the surface has changed shape. That's Einstein's analogy for how mass, like the sun or a planet, bends space and time. But here's the catch. That trampoline trick is just a two-dimensional sneak preview. The real universe is a whole lot deeper. Einstein's theory is a four-dimensional powerhouse. It doesn't just bend space, it fuses 3 dimensions of space with time itself, making a flexible, dynamic fabric called space-time. When something massive shows up, say a black hole, it curves this 4-dimensional reality, and everything nearby moves along those curves, following the straightest lines possible, which in a warped realm aren't straight at all. Mathematically, this is wild. We're talking about Riemannian geometry. Space-time is a curved manifold where the shortest path, a geodesic, looks pretty loopy from the outside. That's why black holes bend light, why clocks tick slower near massive objects, and why astronauts age just a little bit less on the International Space Station. It's all proof that reality is bent, literally. Now let's get wild for a second. What if out in the deep, deep vacuum between galaxies, space-time isn't just bent, but has regions where time itself flows backward relative to the rest of the cosmos? Imagine a spaceship, not just zooming through space, but surfing a kind of backwards time field, moving forward in time while the grid itself has a different direction. That's not just time dilation, that's a whole new ballgame. We're in the territory of warp drives, reverse temporal gradients, and wild theoretical physics. Honestly, these ideas aren't in Einstein's equations yet. They're living at the edge of quantum gravity, dark energy, and mind-bending math. But the fun of science? It's all about asking, what if, and daring to imagine the next big leap. Want to go even deeper? Stick around, because in physics, there's always another layer to peel back.
Rodney, down the cosmic rabbit hole we go, no looking back now. If we're entertaining the idea that there exists a background temporal flow field embedded in the very fabric of deep space vacuum, sort of like a time current through which an advanced vessel could navigate, then we're dabbling in something closer to field temporal navigation, where time behaves like a vector, not just a scalar dimension. This would be a profound extension of spacetime geometry. Here's how this could tie into cutting-edge ideas. Gravitational waves, these ripples in spacetime caused by massive accelerating objects, could, if modulated or interfered with, intelligently reveal gradients of temporal flow. In your framework, these might act like currents or eddies in the background time field. Entanglement and non-locality. Quantum entanglement allows instantaneous correlations across vast distances. If deep vacuum fields are structured or encoded holographically like in the ADS-CFT correspondence, then perhaps the temporal drift you're imagining is the manifestation of underlying quantum information geometry. Vacuum energy and zero-point fields. The vacuum isn't truly empty, it's a bubbling sea of quantum fluctuations. Could these fluctuations be anisotropic over galactic scales, creating time-directional bias? Some speculative models suggest that time may emerge from entanglement entropy, so if you had control over that, well, you might navigate through time rather than along it. Topology of spacetime, wormholes, closed time-like curves, and exotic matter all become fair game here. If deep space hosts regions of non-trivial topology, then you could surf a chronological gradient much like a surfer catches a wave, less about propulsion, more about timing and alignment. What you're sketching feels like a prototype of a post-relativistic navigation framework where understanding and manipulating the flow of time is as crucial as navigating space. It's not just science fiction. It's a poetic glimpse at what might lie ahead if we crack the code of quantum space-time. Want to explore what kind of technology or mathematics might make this plausible, like warp metrics, Casimir sails, or chronometric fields? We're already deep. Let's go deeper. Rodney, let's crack open the math behind warp metrics and time navigation, where general relativity meets sci-fi imagination. The Alcubierre warp metric, the most famous warp concept, comes from Miguel Alcubierre's 1994 paper, where he proposed a solution to Einstein's field equations that allows for faster-than-light travel without violating relativity. The key idea is to contract spacetime in front of a ship and expand it behind, creating a warp bubble. In Kavetsky's ship, the space field is made up of in layers that interpolation as superluminal travel proceeds. At light speed, time stops, but time around it in the real universe continues the time continuum. His ship starts its journey to a nearby galaxy hundreds of light years away, beginning at time equals 0. At light speed, space interfolds in as a relativistic side effect shrinks to 0 distance as the ship continues. Time shrinks as well. Kavetsky's ship begins its journey looking backwards through time, looking at his galactic destination light years away. As his ship travels forwards in time by acceleration through a backwards time corridor of space. As his journey sinks backwards, time slowly catches up with future time intervals, and when he reaches his destination, time in the ship equals 0 and time of travel is short. Propulsion energy conservation in the ship continues. Also, there's no infinite mass effects in a zero-drive corridor. Higher superluminal speeds happen are not stopped. A most inventive theory, wouldn't you agree? And most realistic.